One more scenario you might run into, you might need to take the derivative of a function that's represented by the quotient of two functions. We have a pattern that we can use to find that derivative. So if I want to take the derivative of a quotient, there's lots of ways to think about this. You can see some of these possible notations. I'm going to have a result that is a fraction, a rational expression. The numerator is going to be whatever was originally the function from the denominator multiplied by the derivative of the original numerator minus, you're going to reverse their places, the derivative of the bottom times the original numerator all over the denominator squared. My personal preference, you can feel free to use what works for you. I think of my original quotient as a division between something that's high up and low down. So the high is the numerator and the low is the denominator. So I think of this as low d high minus high d low all over low squared. That sticks in my mind. It's what I use. But again, use what works for you. So the derivative, so it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So we could use a similar function to the one we used for the product rule. If I want to take the derivative with respect to x of 2x cubed plus 5x is my numerator, x squared plus 3 is my denominator, you can see the expression that's written here. So this is the low, the original denominator, times the derivative of the high up, the top. The derivative of 2x cubed plus 5x is 3 times 2 makes 6x squared plus 5, minus the original numerator, 2x cubed plus 5x, times the derivative of the bottom, derivative of x squared plus 3 is 2x, all over the original denominator squared. And I hope that you were thinking that if you were going to simplify this expression, you would make 100% certain that you distributed that subtraction. The very common error when using the quotient rule, don't make it. So I'll do one of these examples from your paper and leave the other one for you to practice on. If I want to find the derivative with respect to x of x divided by x squared plus 1, I'm going to use the quotient rule. Let's use blue. I'm going to write dy dx, or d dx of x over x squared plus 1 equals the original denominator, x squared plus 1, times the derivative of the numerator, derivative of x is 1, minus the original numerator, I never make that line long enough, times the derivative of the denominator, 2x, all over x squared plus 1. Feel free to simplify that. If you're in a free response scenario, feel free to leave your answer unsimplified if you're not. So that's x squared plus 1 minus 2x squared over x squared plus 1 equal to negative x squared plus 1 over x squared plus 1. That's probably the answer you would see if you were if you were on the multiple choice section. That next example I'll leave for you to try so you can practice your new knowledge of the quotient rule. And let's come up here. This last problem, it would be very common to see a problem like this on the AP test. So how about I do 2 of these and leave the other 2 for you. So in each case, we've been given a function f of x that seems to be in the style of some of these functions that we've learned to take derivatives of in this lesson. And we've been asked to find f prime of 2. So remember my warning to you. Do not try to tell me what f prime of 2 is until you can first write me an expression for f prime of x. So let's do this first one. If f of x is 2 times g of x plus h of x, I see a sum. So I know I can take the derivative of f by adding together the derivatives of the 2 addends in this sum. And I see that the derivative of 2 times g of x, well, that 2 is a constant multiplier. So that 2 is going to hang out and still be a multiplier times whatever the derivative of g is. Well, the derivative of g is called g prime of x. Plus, because I said I could use the sum rule here, the derivative of h of x is called h prime of x. Now, when it's time to find f prime of 2, I do that by replacing all of these x's with 2's. But now look what I can do. I have expressions, I have values for these expressions. 2 times g prime of 2, I've been told is -2. H prime of 2, I've been told is 4. So I'm going to be able to simplify f prime of 2 is -4 plus 4, which is 0. Cool. I'll do one more and I'll leave the other 2 for you. Let's do that middle one. So I know f of x is g of x times h of x. That tells me I have a product that I want to take the derivative of. I'm going to use the product rule. So f prime of x, the product rule, the first function, so you can imagine a little invisible multiplication dot there. The first function, which was called g of x, times the derivative of the second, well, the derivative of h of x would be called h prime of x, plus the second function, h of x, times the derivative of the first would be called g prime of x. All right, well now how do I find f prime of 2? F prime of 2 is going to equal g of 2 times h prime of 2 plus h of 2 times g prime of 2. And I have values for all of those. So f prime of 2 is going to equal g of 2 is 3 times h prime of 2 is 4 plus, that's a plus sign, h of 2 is -1 times g prime of 2 is -2. So f prime of 2, the thing I was asked to compute, is 12 plus 2, which is 14. We will find soon enough that we will have many occasions on which we find it convenient to take the derivative of a derivative. So the derivative of a derivative is called the second derivative, and we use this notation, y double prime. So the derivative of y prime is called y double prime, and that's y with the 2 little hash marks. Or you could call it d squared y dx squared. Notice how the 2's don't show up in the same place. So that's an important part of the notation. Make sure you pay attention to. Let's do this first example on your page. This would have been much more convenient if I had just gone ahead and given this function a name. So let's pretend that this function, let's see what we got. Let's pretend that I had called this function y. Feel free to do that. Feel free to name functions that you would find it convenient to have names for. So notice I'm not going to be able to find the fourth derivative until I find the third derivative. I can't find the third derivative until I find the second derivative. You can't find the second derivative until you find the first derivative. So I'm going to start by finding y prime. That's the first derivative. I could have also called it dy dx. It's going to equal, that 8's going to multiply the -5, so -40, x to the 7th, plus 6 times 2 makes 12, x to the 5th, plus 32. Where does the -1 go? The derivative of 1 is 0. So I have one fewer term in my derivative than I did in my original function. Now that I have y prime, I can find y double prime. I'm writing nice and big so you can see. 7 times -40 is -280, x to the 6th, plus 5 times 12 multiplies to make 60, x to the 4th. What happens to 32? The derivative of 32 is 0. So I have just 2 terms in my second derivative. Y triple prime, I'm going to have to stop and figure out what 6 times 28 is. All right, so y triple prime is going to equal, this 6 is going to multiply -280 to make Negative 1680 x to the fifth plus the 4 is going to multiply 60 to make 240. X to the exponent is 1 less. X cubed. I've been asked to find the fourth derivative, so I'm getting much closer. The fourth derivative, remember we use a 4 up here instead of 4 hash marks. That's going to equal, okay, 5 times 168. I'm checking my calculator. Negative 8400 x to the fourth plus 3 times 24, 720 x to the second. That's one exponent, 1 less. So try those other two problems. Remember, you're not going to find the second derivative until you take the first derivative. But that last problem, I've given you the fourth derivative. So what are you going to do to find the fifth derivative? Don't let that last one freak you out. It's shorter than you might fear.